Let we have a discussion about the homonuclear diatomic molecule from lithium Li2 to neon Ne2. There two kinds of MO diagrams are there. Which are those MO diagrams? What SP mixing is? That let we know first. By interaction between atomic orbitals, molecular orbitals result. Atomic orbitals remain with one nuclei for each orbital, while molecular orbitals remains with two or more nuclei for each orbital. So influence of many nuclei remain. So they remain polycentric, and depending upon the kind of interaction, type of interaction, as per our LCAO principle, energies of molecular orbital varies. Means if we consider bonding kind of interaction, additive interaction, constructive interference, attraction will be there between the nuclei, more electron density will be there between nuclei, and due to that energy of that orbital decreases, while if we consider destructive interference, the energy of antibonding orbital will increase. So bonding, antibonding orbitals resulted due to the overlap of respective atomic orbitals. That arrangement we need to study. So sometimes there remains no interaction. Why? Maybe there is equal bonding and equal anti-bonding interaction, or the orbital is so inner that there is a no appreciable overlap. In such cases, non-bonding orbitals also do form. So non-bonding orbitals, bonding orbitals, anti-bonding orbitals, these are the molecular orbitals. How can we arrange them in the increasing order of energy? Representations of energy levels of various molecular orbitals is none other than molecular orbital diagram. To construct or to establish that molecular orbital diagram, we do consider three compartments. Left compartment, atomic orbitals of one atom, and right compartment, atomic orbital of other atom. Orbitals from those two atoms will interact in different ways following LCAO principle to produce various molecular orbitals, and those molecular orbitals we represent in central compartment, middle compartment, in increasing order of energy. To represent the increasing order of energy, we show energy arrow to the left side or to the right side of molecular orbital diagram. And most important thing, the chemistry depends upon the electronic configuration, electronic distribution. Then how do we distribute electrons in molecular orbitals? By following Bohr principle, by following Hund's rule of maximum multiplicity and Pauli's exclusion principle. Bohr principle means electron filling takes place from low energy orbital to high energy orbital. Hund's rule of maximum multiplicity means electron pairing will not occur till the orbitals of same energy level are completely half filled. And last, Pauli's exclusion principle means no two electron in an orbital will be with same spin. They will be paired. Their spins will be opposite. Considering these all basic facts, we can construct or develop molecular orbital diagram. Let us see what kind of molecular orbital diagrams are possible for diatomic molecules from lithium to neon. Actually, two kinds of the molecular orbital diagrams are possible. One where more influence of sp mixing is there, and other where there is a no more change in energetics due to sp mixing is there. Let us see one by one. This is a one kind of molecular orbital diagram applicable for diatomic homonuclear molecules from lithium to nitrogen. Means for lithium, beryllium, boron, carbon, nitrogen, we follow this MO diagram. Let us understand how this MO diagram is constructed. Basically, oneness orbitals from each atom are of low energy. So they should interact to form bonding and anti-bonding. But because of their innerness, their appreciable overlap is not there. due to which they remain non-bonding. They are not represented in this diagram. Our diagram talks about 2s and the higher orbitals. 2s orbital of one atom, which is represented left side. 2s orbital of other atom, represented right side. See their energies. Energy level is same, means those are of the same element. Those are of the atoms of same element. If two atomic orbitals do combine, two molecular orbitals, one bonding and one anti-bonding. Bonding orbital is of low energy and is represented by sigma. Anti-bonding orbital is of high energy and represented by sigma star. Now main point. Three 2p orbitals are represented left side. By the way, three 2p orbitals are there to right side. Their orientations are along x-axis, y-axis and z-axis. I told you in the previous video what is a conventional way of understanding about the bond direction. What we consider the bonding along which axis? Z-axis. So pz orbital of one atom, say left atom, will interact with pz orbital of other atom in axial way, and the symmetry of pz orbital is sigma. So it will produce two molecular orbitals. One sigma of lower energy, that's our bonding molecular orbital, and other sigma star anti-bonding molecular orbital, that is of higher energy. If you read this diagram, you will find sigma decreases by little amount and sigma star increases by more amount. I come to that point. Let us discuss other atomic orbitals and their interaction. 2px and 2py orbital from one atom. 2px orbital from one atom interacts with 2px orbital of other atom. Symmetry of 2px is pi category. To produce bonding pi orbital, pi to px, and anti-bonding pi orbital, pi star to px. The energy with which the bonding orbital decreases, with that much amount of energy anti-bonding orbital is increasing. It's a general approach for molecular orbital diagram. Similarly, 2py orbital from one atom will interact with 2py orbital of other atom to produce bonding pi to py and anti-bonding to py, means pi star to py. The energy of pi to px and pi to py is same. Those are degenerate. And energy of anti-bonding pi star orbital is also same. Those are of the same level. Main point is sigma to pz orbital is of higher energy than that of pi to px and pi to py. In true sense, head-on-head interaction, direct interaction, axial interaction should be stronger compared to lateral interaction. So, stability governed by the resultant molecular orbital, that's a bonding molecular orbital, that's a sigma to pz, should be more. If stability is more, then energy should be more lower. So sigma to pz orbital should be of lower energy than that of the pi to px and pi to py. But what is the reality in this diagram? Sigma to pz is of higher energy than pi to px and pi to py. About antibonding orbital, there is no difference. What are we finding? Pi star to px and pi star to py, those orbitals are of lower energy than that of the sigma star to pz. Because of strong interaction, sigma star to pz orbital is more unstable, increased in energy. So here strong sigma interaction is revealed, but it is not revealed in the bonding orbitals. It is because energy gap between 2s and 2pz in case of atoms, lithium, beryllium, boron, carbon and nitrogen is small, due to which interaction between obtained molecular orbitals also occurs. Orbitals of same symmetry interacts with each other to change their energies. S molecular orbital interacts with P kind of molecular orbital, so we say it as sp mixing. sp mixing in such low atomic bearing elements is in such a way that sigma to pz is of higher energy than pi to px and pi to py orbitals. True sense how energetics is decided that you will get clear next year. Time being, try to understand this point. Because of small energy gap between 2s and 2p, this energetics is there. Now question arises, why there is a small energy gap? Because these atoms have low atomic number. Nuclear power is not that much strong, and because of the less nuclear power, the separation between 2s and 2p remains poor. Therefore, energy levels are near. So this is a MO diagram we need to follow for low atomic numbered molecules right from Li2 to N2, where pi orbitals are of low energy than sigma to pz. It is called as sp mixing diagram. Let us understand what is the other kind of diagram. This is the other kind of MO diagram. It looks spacious. See, as usual, 1s orbital, those are inner orbitals, those do not undergo appreciable overlap, so will remain non-bonding, are not represented here in this MO diagram. We are starting from 2s orbital onwards. 2s orbital of one atom interacts with 2s orbital of other atom to produce one bonding, one antibonding represented as sigma and sigma star. Out of the three 2p orbitals, the 2pz orbital, which is along the internuclear axis, will undergo head-on-head interaction, axial interaction, strong interaction, due to which bonding orbital will decrease by more extent. Accordingly, antibonding orbital will increase by equal extent. And pi interaction, which is resulted due to px and to py orbitals from each atom, will result one bonding pi orbital and antibonding pi orbital called pi star. Energy of sigma to pz is lower than the pi to px or pi to py. Why? Because sigma orbitals to pz orbitals experience strong interaction, so its energy decreases, which was a not case in the previous situation. There, energy of sigma to pz was higher. Now here, why not energy of sigma to pz is disturbed? Because we are talking about the diatomic species which are formed by those atoms whose atomic number is high, whose nuclear power is high, whose nuclear charge is high. In case of oxygen, 8 protons are there, for fluorine 9 and for neon 10. Because of high nuclear power, separation between 2s orbital and 2p orbitals remains more. Energy gap between 2s and 2p orbitals remains appreciably more, in order that sigma to pz peacefully remains at low energy level. What was happening in the previous case? 2s and 2p energy gap was less. It is actually a simple approach for establishment of MO diagram, and this MO diagram we can apply for oxygen molecule, fluorine molecule, neon molecule. Are these two types of molecular orbital diagrams clear? This is at a glance representation of various molecular orbitals and their energy levels. Very left side you will find representation of lithium molecule, then beryllium molecule, then boron molecule, then carbon molecule, and where red color rectangular orbitals are represented, that's first set is nitrogen molecule, next is oxygen molecule, where crossover is there, crossover of energy level of 2pz to pi to px and pi to py is there. At nitrogen, 2pz orbital is of high energy compared to pi to px and pi to py. But for oxygen, sigma to pz orbital is of low energy than pi to px and pi to py. That's called crossover, order of energy level change. And then for fluorine and neon, what are the order for oxygen is there?
that remain in continuation. If you observe the energy gap between sigma star 2s and the p orbitals, you will find as we move from left to right, the energy level of sigma star 2s decreases because energy of 2s orbital, atomic orbital I am saying, decreases as we move from left to right. And due to that decrease, and due to which peacefully sigma to pz can be of low energy in case of oxygen, in case of molecules oxygen and higher atomic number bearing molecules. Crossover diagram is a general explanation I am giving. True explanation on the basis of symmetry, on the basis of LCAO method, on the basis of interaction, you will understand more correctly next year. Is this energetics and consolidated MO diagrams clear?
Students, today a difficult question I am asking to you. If you could answer this question with understanding, then you have understood molecular orbital treatment, and next year studies will be very easy for you. See, we have studied the homonuclear diatomic molecules, their MO diagrams, and molecules were from lithium to neon. But for low atomic numbered molecules, means from lithium to nitrogen, we follow one kind of MO diagram, and from oxygen onwards, we follow the other kind of MO diagram. In low atomic number diatomic molecules, we say that sigma to pz is of higher energy than that of the pi to px or pi to py orbitals. Why do we say that sigma to pz is of higher energy? Because of interaction of two molecular orbitals or interaction between two molecular orbitals. So that sigma to pz orbital interacts with which molecular orbital so that its energy increases and other orbital energy actually decreases, but we could not recognize in this MO diagram. One hint I give it to you. See the symmetries of molecular orbitals, you will get the answer. I repeat, I want answer from you the name of that molecular orbital which interacts with sigma to pz so that sigma to pz energy increases. Name that orbital in the comment box. Yes. So two kinds of MO diagrams about which now insight is clear. Let us apply our knowledge to explain molecules from Li2 to Ne2 stepwise, part-wise. Means first Li2 molecule, then B2 molecule. Means how molecular orbital treatment can help us to explain the chemistry of those homonuclear diatomic molecules. Let us begin from next part.